All right, welcome. Today we are putting on our detective hats and heading straight into the lab. What's the mission? Well, we're going to solve the case of how to turn some pretty ordinary chemicals into these absolutely gorgeous, vibrant blue crystals. But first, let's figure out why on earth we'd want to do that.
So, why should you care about a bunch of blue crystals? Well, if you've ever been in a garden center, you might have seen this stuff. It's called Bordeaux mixture. It's used to protect plants like grapes from fungus. And guess what the key ingredient is? Yep, it's the exact copper sulfate we're about to make. So, from the lab bench to the vineyard, it all starts right here.
You know, every good detective story is all about transformation, and this one is no different. We start with some really unassuming materials, just this plain black powder, that's copper oxide, and a totally clear liquid, sulfuric acid. But with a little bit of chemistry, we're going to turn them into these incredible jewel-like blue crystals. It's a total chemical makeover. So what's the secret formula, the blueprint for our investigation? It's all right here in this one equation. We're taking copper oxide, which is a base, and we're reacting it with sulfuric acid. Now, when you mix a base and an acid, they neutralize each other. And what do we get out of it? Our target, copper sulfate, which is a type of salt. And a little bit of plain old water. This neutralization reaction is the heart of this entire operation. Okay, let's get into part one of our mission, forging the solution. This is where we take our raw ingredients and kick off the reaction that's going to lead us to those amazing crystals. So the procedure starts. First, we measure out our acid. Then we give it a little gentle heat. Then, bit by bit, we start adding the black copper oxide powder. And as we stir, you get to watch the magic happen. The black powder just disappears, and that clear liquid starts turning this brilliant blue. But that leads us to our very first clue. Why even bother with the heat? Couldn't we just, mix them at room temperature and call it a day? This is actually a super crucial step in our chemical investigation. What is the heat really doing? And here is the answer. It's all about energy. Warming up that acid is kind of like giving the particles a shot of espresso. It makes them zoom around way faster, which leads to more collisions and, more importantly, more successful collisions. And more successful collisions just means a faster reaction. So we're warming it up for one reason: speed. Now check out this key instruction right here. We're told to keep adding that black powder until it just stops disappearing, until we see some leftover black stuff at the bottom. In chemistry, we have a name for this. It's called adding a substance in excess. And this brings us to our second big clue. Why on earth would we intentionally add too much of one ingredient? I mean, it seems wasteful, right? But in chemistry, it's actually a really clever strategy. So what's the master plan?
It's actually a brilliant move to guarantee purity. See, by adding way more copper oxide than we need, we make absolutely certain that every single last molecule of that dangerous sulfuric acid gets used up. If there were any acid left over, it would just be an impurity, contaminating our beautiful final crystals. So we're sacrificing a little bit of powder to protect the final prize.
All right, our reaction is done, but our job is not over. We've got a brand new problem: all that leftover black powder. So welcome to part two, the great purification. Okay, so we've got this beautiful blue liquid, but it's all mixed up with this unreacted black sludge. The solution? It's simple, it's elegant: filtration. We're just going to separate the solid that we don't want from the liquid that we do. Before we go any further, let's get our detective lingo straight. The liquid that actually makes it through the filter paper, that's called the filtrate. And the solid gunk that gets left behind, that's the residue. Two key terms you got to know for any purification mission. So let's apply those terms to our case. The filtrate is our prize. It's that pure blue copper sulfate solution that we've been working for. And the residue? That's just the leftover black powder. Hey, it did its job. It neutralized all the acid, and now, thanks to filtration, we can get rid of it cleanly. We are one step closer to perfect crystals. And now for the grand finale. We've got our pure solution. It's time to pull solid, beautiful crystals out of what looks like thin air. Let's move on to part three, the magic of crystallization. The secret to this whole magic trick is hidden right here in this data. This table shows us something called solubility, which is just a fancy way of saying how much copper sulfate can dissolve in water at different temperatures. Now look at these numbers. At about room temperature, 20 degrees, you can dissolve 32 grams. But
Crank the heat all the way up to boiling, 100 degrees, and that number jumps to 114 grams. The hotter the water, the more stuff it can hold.
Let's just visualize that for a second, because the difference is pretty dramatic. At boiling point, 100 degrees Celsius, water can hold a massive 114 grams of copper sulfate. But just cool it down to room temperature, and bam, it can only hold 32 grams. That is a huge drop. And that difference, well, that's the key to everything.
So what's going on here? Okay, imagine the hot water is like a big sponge that's holding a ton of dissolved salt. As that water starts to cool down, the sponge basically gets smaller. It just can't hold as much anymore, so it's got to squeeze the extra out. And that extra that gets squeezed out, that's our copper sulfate, and it forms these perfectly structured solid crystals. All right, time for our final clue, and this is a question that really separates the good chemists from the great ones. If we want to get the solid out, why not just take a shortcut? Why not just boil off all the water really, really fast? I mean, it seems logical, right?
And here is the big reveal. It turns out that beautiful blue color isn't just from the copper sulfate. It's because water molecules are literally locked into the crystal's structure. Think of them like tiny little gems that give it its color and shape. We call this the water of crystallization. Now, if we boil the solution dry, we violently rip that water out, completely destroying the structure. And instead of blue jewels, we're just left with this dull white powder. We want the treasure, not the dust. So, we have solved the case of how to make the crystals. But a true chemical detective knows that how you work is just as important as the results you get. Which brings us to our final part, the chemist's code. The first rule of the code is always safety first. We are working with sulfuric acid, which is an irritant, and copper compounds, which are harmful. That means eye protection is completely non-negotiable. These symbols you see, they're not suggestions, they're commands. So let's quickly review the code we've learned today. 1. Protect your eyes. 2. Never boil the acid because it can spit and cause some really serious burns. 3. Use a water bath for gentle, controlled heat. And finally, when you're ready to dry your crystals, do it gently with filter paper, not in a hot oven that would just destroy their beautiful structure. This is the path to getting those perfect results. And that pretty much closes our case. We've learned that to create these large, perfect crystals, the key is to cool the solution slowly. Patience is literally rewarded with beauty and order. Which kind of leaves us with one last thought. If slow, patient growth creates perfection in chemistry, what else in nature, and maybe even in our own lives, grows better with just a little more time and a whole lot more patience?